Thank you for coming to my dissertation defense. My dissertation is titled with Electrochemical Reactions of Quinones at Conducting Polymer Electrodes. So the presentation will be divided into two sessions. First, I will introduce the motivation, the goal of the thesis, and then background information about materials and methods, then followed by the results in the form of 4 papers. First, energy concerns everyone, especially in the past centuries. The global energy consumption increased rapidly due to the population growth and the industry development. And also we can see that the structure of energy has been optimizing all the time, but still until 2017, fossil fuels together with traditional biofuels are still the major fuel consumed, up to 94%. And we know that fossil fuels, they are unrenewable fuels, and also the use of fossil fuel, including natural gas, crude oil, and coal, and biofuels, they are through combustion process produce a lot of carbon dioxide gases, and that is the main reason for the climate change. So clean and renewable energies are attracting more and more attentions, including hydropower, nuclear, wind, solar, these things. In the meanwhile, converting the chemical energy stored in the forest and the fossil fuels into electricity directly without combustion process, without carbon dioxide emission, is also in demand. And this is not just a colorful dreams, it's a promising future with the energy generation device such as fuel cells. This is the structure of fuel cells. It consists of 2 electrodes and separated by a membrane. Fuels are fitted in one side and get oxidized under the catalyst. Electrons flow through the out circuit and form electricity. The electrons get captured by the oxidizer in the other side under the catalyst. So we can see that the oxidation of the fuel and also the reduction of the oxidizer both need catalyst materials, which is typically platinum-based. And that is the main reason limiting the commercial use of this device, because platinum is a expensive noble metals. Also, conducting polymer arise as a new class of materials for electrocatalysis because of a lot of advantages. For example, they are highly conductive, as mentioned by Professor Rapkowski. They are based on abundant atom elements. They are solution process porous, and also they don't form insulating oxide layers and can survive in strong acid and so on. So our interest is to study the electrochemical reactions of the reactant derived from the forest on the conducting polymer electrode, and for the application in electrical energy device mainly. In the following slide, I will first introduce the materials, first conducting polymers. As mentioned also, polymers were thought to be insulators for a long time, and conducting polymers were the most recent generation of polymers. They were found, the first generation was found to show surprisingly high conductivity after doping process, but they are not stable in air. But after that, conducting polymers become popular and intensively investigated. And until now, there are a few types important conducting polymers, including polypyrrole, polyalanine, and P-dot, and so on. Conducting polymers, they are featured with a single-double structure called conjugation structures. The pi electrons are delocalized among the polymer backbones and result in some conductivities. But the conductivity of intrinsic conjugated polymers was still low, span the range from insulator to semiconductors. But this can be increased a lot by introducing charge carriers through doping process. can reach up to metal conducting regions. The doping process of conducting polymers involves removing electrons from the polymer or adding electrons to the polymer, which is called the p-doping or n-doping process, respectively. To compensate the charge at the polymer backbones, counter ions will be withdrawn from the surrounding environment. P-dot, as also mentioned, is the most successful and commercial conducting polymers now, and thus, of course, is our interest. Neutral P-dot characterized with aromatic structures and is not conductive. While doping process, it generates polaron and bipolarons. Also accompanied with this doping process, there is a color change from dark blue into light blue. Different synthesites introduce different counter ions and result in different morphologies as well as properties. In this thesis, we have used P.TOS and P.PSS. P.TOS was polymerized from E-dot monomer in presence of ion tosylate and pyridine, while P.PSS was prepared from suspension consisting of pH 1000, dimethyl, glycerol, and GOPs with an optimized ratio. The resulting conducting polymer P.TOS shows higher electrical conductivity in comparison with P.PSS due to higher crystallinity and also higher Typhine sulfonate ratios. But P.PSS presenting higher proton mobility compared to P.TOS due to the protons in the PSS. Besides that, due to the smaller size of tosylate ions, tosylate ion is mobile counter ion during the charge and dodge process and can be exchanged by other small counter ions, small anions, while PSS is a polyanion, and especially with the presence of GOPs, which is a cross-linker, so they are not mobile and exchangeable. This mobility of the counter ion and the exchangeability will result in different ion transport upon polarization. For example, in P.PSS electrode, if we apply a negative voltage to de-dope the polymer and then to keep the charge neutralizations, this counter ion tosylate will be leaving the polymer. And in the case of P.PSS, because PSS is not mobile, it will be cations coming into the polymer, result into this different ion transport in these two polymers. The effect we will discuss more in the result session, and now we come to the materials of the fuse. Lignin is a potential cheap fuse because it forms important structural materials of the woods and also is the second abundant biomass in nature, exceeded only by cellulose families. In particular, the current paper and pulp industry, they take cellulose for paper making, but release lignin rich waste called black liquor, around 100 million tons per year. That equals 68 million tons of dry lignin mass. So lignin in particular is super renewable and also cheap fuel at hand we have now. The chemical structure of lignin differs from woods to woods, but in general, they have these complex network structures and it is insoluble in water. Sulfonate lignin, or lignin sulfonate, is soluble in water due to the introduction of these hydrophilic sulfonate groups. And upon oxidation, the phenolic moieties can be oxidized to these cyclic diurnal structures and can undergo to proton to electron transfer reactions reversibly. But you can see that there are also other electroactive groups, so the energy density of lignin sulfonate need to be increased further. And this was also promising. For example, in this group, they do hydrolysis of craft and get catechol with a yield up to 7%. In this thesis, in our thesis, we have used catechol, hydroquinone, tyrone, alizanin. Tyrone and alizanin, they are also quinones, hydroquinones, but carries negative charge when dissolved in acid electrolyte. More information will be discussed in the results session. Electrochemical method is a main technique we use throughout the whole thesis. Most experiments were carried with this 3 electrode cell consist of a platinum as a counter electrode, silver chloride as a reference electrode, and also a working electrode. About the working electrode, we have put the p-dot TORS or p-dot PSS mounted on a metal modified glass. We have also used platinum disc, glassy carbon disc electrode. And for kinetic studies, the disc electrode was connected with an electrical motor to have the rotating speed precisely controlled. So next, coming to the results session. First, we studied the electrocatalysis of a generic quinone reactions on conducting polymer and for the application in fuel cells. These two proton to electron transfer reactions featured with a oxidation and a reduction peak on glassy carbon electrode in the water membrane. The peak-to-peak separation delta E and the peak current can give us some information about the reaction rate. For a 2 electron reactions, this delta E is about 30 millivolts, and the current ratio should be close to 1, and both of these 2 parameters will be independent on scan rate. On glassy carbon electrode, we found that is quite irreversible because the peak-to-peak separation, even though at a low scan rate, is quite high, around 100 millivolts, even though the current ratio was almost 1 and independent on scan rate. The reversibility was even less on platinum electrode because higher peak-to-peak separation and also the dependence on scan rate. And a little higher reversibility was found on p-dot TORS because the peak-to-peak separation was smaller at low scan rate. Here is also independent on scan rate, but the peak-to-peak separation increased dramatically with the scan rate. On p-dot PSS electrode, we observed the smallest peak-to-peak separation at low scan rate, around 30 millivolts. And both the peak-to-peak separation and the current ratio, they are almost independent on scan rate. Or in other words, we observed the largest reversibility on p-dot PSS electrode. This is very interesting because consider the electrical conductivity, p-dot PSS has the smallest electrical conductivity, which in the other words, the performance shows that the efficient proton conduction is very important for these reactions that makes p-dot PSS the best electrode. We further prove this by doing the experiment in electrolyte of different pH. With the increase of this pH, the peak position shifts to negative values predicted by the Nernst equilibrium. That makes sense. But also we observed that this peak-to-peak separation increase, the peak current decrease. So when the proton concentration in the electrolyte becomes lower, the reaction rates also decrease, which further emphasize that this efficient proton transport is super important for these 2 proton to electron transfer reactions that makes p-dot PSS prior to the other electrode. Another advantage for this p-dot PSS electrode is, as a polymer electrode, we found that even for a thin p-dot PSS film, about 100 nanometer, we get the comparable peak current to platinum electrode. And this peak current can be further increased by simply increase the thickness. So the reactant have access into the bulk of the polymer, and this is really good for large-scale applications. Then we use this simple etch cell to demonstrate this hydroquinone oxygen fuel cell. Hydroquinone was dissolved in sulfuric acid as a fuel. We have tried different electrode material in this site. In the other site, oxygen was used as the oxidizer, and platinum was used as the electrode. The results shows that on P.PSS electrode, we observed the smallest voltage loss, and also it yields the highest maximum power, followed by P.TOS electrode, glass carbon electrode, and the least on platinum electrode. The result from device level is in good agreement with the initial electrochemical studies. So in this paper, we found that for these two proton to electron transfer reactions, this proton transport is a rate-determined step, and that makes P.PSS excellent electrode materials due to the efficient proton conductions in the PSS. In the second paper, we studied the adsorption of lignin sulfonate onto conducting polymers and the mechanisms, as well as large-scale application. So first, film electrode was used in this experiment. In pure electrolyte, P.TOS characterized with a typical capacitive current in the voltmicron. And when lignin sulfonate was added in the electrolyte, we observed an oxidation peak and a reduction peak due to the reactions of the quinones in the lignin sulfonate. What's interesting is when we take the electrode out and rinse it carefully and use it in a pure electrolyte without lignin sulfonate, the peaks were still there. So it means that lignin sulfonate was somehow adsorbed or blocked onto the polymer. And we also found that on P.PSS electrode, there are less lignin sulfonate adsorbed, as shown by the smaller peak current here. The difference on P.PSS and the P.TOS was considered as a result of ion exchange, and we demonstrate also in the paper by QCM. As mentioned, lignin sulfonate is a polyanion. It carries a negative charge when dissolved in electrolyte. So at P.TOS electrode, when this tosylate ion was moving out, it will have a attraction force to attract lignin sulfonate molecules into the polymer, while in the case of P.PSS, as PSS is immobile and carries a negative charge, so it will repel lignin sulfonate out. There will be less lignin sulfonate adsorbed. Besides that, we also studied the effect of pre-incubation time on the adsorption. Shown by the integral charge, we found that the lignin sulfonate adsorption increased with longer incubation time, and after 5 or 6 hours, it starts to get saturated. So, which means that this can be guidelines for lab treatment. It's just interesting for us. But it's not clear that whether this adsorption is driven by this electric field or is a spontaneous process. But by this UV spectroscopy, we demonstrate is also a spontaneous process, as shown by the peak around 280 nanometer for the sample without electric field application. In a above experiment, the film electrode was used, and that was fabricated from organic solvent, which is a slow process and not good for large application. So for large application, we want to optimize this process in aqueous solutions. First, P-dot nanoparticles with small and exchangeable counter-ions was fabricated from E-dot monomer in presence of ferric chloride and sodium hyposulfite. Then this product was washed carefully and mixed with lignin sulfonate for some time to get P-dot lignin sulfonate composite via ion exchange process. Here is a picture of the products. Is ready for screen printing, job casting, other large-scale applications. And also this charge plot shows that lignin sulfonate was successfully incorporated with p-dot nanoparticles, as shown by the increase of the charge capacity from 23.7 to 44.6. So in this paper, we studied the adsorption of lignin sulfonate on p-dot polymer and found that it's strongly affected by the counter ions. It's affected by the pre-incubation time. It's also an automatic spontaneous process due to concentration gradient. We have also optimized the synthesized rules in aqueous solution to get p-dot lignin sulfonate composite via ion exchange, and that is good for large-scale application. The ion exchange mechanism also inspired us to study more about the effect of this reactant on conducting polymers, for example, for charge reactant and its potential applications. Due to the mobility of the counter ion, it's reasonable to assume that for a neutral reactant, they will have no effect. So neutral reactant will have both similar access into the bulk of the polymer, and the reaction will not affect it. But for charged reactant, for example, negative charged reactant, it will be much easier to go inside p-dot TOS polymers due to the anion transport, but much more difficult to go into p-dot PSS polymers, and so on. This redox of this redox reactions of this reactant will also affected. In paper 3, we take two model molecules. The first one is catechol. The other one is tyrone. Catechol is electrically neutral when dissolved in acid electrolyte, while tyrone carries two negative charge due to this group. We found that for catechol, it presents similar peak current on both electrodes, with slightly higher current at p-dot PSS electrode due to the efficient proton transport, as we discussed in paper 1. But on tyrone molecule reactions, we found that the peak current was significantly suppressed at p-dot PSS electrode, but enhanced dramatically on p-dot TOS electrode. This initial result shows there is a ion-selective electrocatalysis, as mentioned before, and we studied the kinetics to prove that exchange current can be a probe for the reaction rate. The larger the exchange current, the faster the kinetics or the reaction rate. We found that on neutral catechol, both these two polymers, they show kind of similar or close values of the exchange current. But on negative charged tyrone molecules, on p-dot PSS, the exchange current was significantly small, while on p-dot tosylate, it was about 2 orders larger. So further proves the ion-selective electrocatalysis. And so to summarize, we have shown that tyrone redox at the p-dot TOS has this highest electrocatalysis, and followed by the others. And keep this insight, we picked two negatively charged molecules, alizanin and tyrone, for the organic redox flow battery measurement. Tyrone was used as a pozolite because it has a relatively high redox potential. Alizanin was used as nectite because it's low reduction potential, redox potential. Together, we are supposed to get 0.8 volts from the batteries. This is how the device looks like. Carbon paper was used as electrode material in both sides first, and we then loaded this carbon paper with p-dot PSS and p-dot TOS layers for comparison experiment. From the charge-discharge result, we can see that On the cell with p dot TOS layer, we get the smallest voltage loss and also getting the highest charge capacity around 22 milliampere hours, followed by p dot PSS cell and the least on the bara carbon cell. So from device level, it further proves that the existence of ion selective electrocatalysis. So in this paper, we studied the ion selective electrocatalysis at p dot polymers and found that for a negative charge reactant, the reaction will be enhanced at the p dot TOS electrode, but it will be suppressed at PSS electrode, and no effect on neutral reactant. In the last paper, we studied the proton management in catechol reactions with p dot polymers. As mentioned, that this catechol oxidation and the reduction of its corresponding quinones involves protons. So the release and the neutralization of protons will affect the actual pH in the interface. But in buffered electrolyte, because this buffer component can offset the actual pH change very quickly, so the pH will change little, and in return, it will affect the redox chemistry of the catechol very small. But in unbuffered electrolyte, the pH change will remain, and also this remained pH change will have a larger effect on the catechol reactions. To know exactly what's happening at the conducting polymer p dot TOS and the p dot PSS with a different anion different ion exchange, we did the experiment in buffered, unbuffered electrolyte. First, in buffered electrolyte at p dot TOS electrode, we observed this typical oxidation and reduction peak. And with the increase of pH, we are supposed to see the peak potential shift to negative values due to the proton electron numbers. And by plot this potential versus pH, we are supposed to get the Polymer diagram. For catechol reactions, the theoretical Polymer diagram consists of 3 slopes for the equilibrium. In the acidic region, the slope is close to 0.59 volts, followed by 0.3 volts, and then a 0 slope for a fully deprotonated catechol reaction to quinones. This is the result we found on p dot TOS. And you can see, indeed, there are 3 slopes corresponding to the theoretical plot, but also we found that the transition point shifted to low pH values. And for example, the first transition point happens at a bulk pH around 6.7, which should happen at first pK value around 9.5. So it means that when the bulk pH was still 6.7, the interfacial pH has already reached 9.5. So in other words, the interfacial alkalization happens at this p dot TOS electrode due to the anion exchange from the buffer component. For example, the proton accept from the buffer. At p dot PSS electrode, in the other hand, oppositely, we observed the first transition point shifted to high pH values around larger than 12, which means interfacial acidification in p dot PSS due to the proton conduction from the buffer component in p dot PSS. In unbuffered electrolyte, we observed that when the pH was larger than the proton concentration, the potential becomes almost independent on pH at these 2 electrodes. So a similar larger decoupling effect was observed on these 2 electrodes. And in this case, because the proton equilibrium was not established, so it's controlled not by the thermodynamic, but by the proton transfer kinetics. So to summarize, in this paper, we studied that in buffered electrolyte, this reaction results in an interfacial alkalization at p-dot Torus electrode and an interfacial acidification at p-dot PSS electrode. In unbuffered electrolyte, a similar and larger decoupling effect of the interfacial pH to the bulk pH was found due to proton transfer control. That's the main part of the presentation. So to summarize, we studied the key role of PSS in promoting the rate-determining proton transport in hydroquinone redox reactions. We studied the lignin-sulfonate incorporation into p-dot and optimize the synthesize rules for large applications. We also promote and demonstrate the concept of ion selective electrocatalysis of catechores in p-dot PSS in p-dot electrode. Sorry. We have also studied the proton management of this reaction at the p-dot electrode and observed a surface alkalization at p-dot Torus, surface acidification at p-dot PSS, respectively, in buffered electrode, buffered electrolyte. In unbuffered electrolyte, a similar and even larger decoupling was observed. In the future, we would like to investigate more about the redox chemistry of other quinones and quinone-based biopolymers at conducting polymer electrode and the corresponding mechanisms and the application in electrical energy device. And also, due to the last paper, we would like to investigate more about the electrical interface phenomena of the existing electrodes and developer strategies to overcome the interfacial decoupling of the pH from the bulk media. Okay. Yeah, with that, I'd like to thank you, my supervisor, Xavier Crispin, and my co-supervisor team, including Mikhail, Magnus, Victor, and the other big families, including those who are here or not here. Thank you all for your attention.